All right, so we'll get started with, we're dealing with springs and Hooke's law, and we're going to talk about simple harmonic motion. Do you remember what Hooke's law was? So he said that the force of a spring, and I'm just going to write it in one dimension. So think of it as the x direction or something like that, or y. Is negative k x minus x naught, or something like that. This would be the force in the x direction of a spring. This is the spring constant. And then this is the distance stretched from its equilibrium point. Minus sign means that it opposes the stretching. Okay, the force does. So if I stretch in one direction, the force is in the opposite direction. Or compress it in one direction, the force is in the opposite direction. So magnitude of the spring force is probably the easiest way to remember it. It's just k times the distance stretched, where k is that spring constant. Okay, and then when you can deal with vector forces, you know, when you draw the free body diagram, you'll see the vectors. You'll put in whatever signs or directions you need by hand. But you know the magnitude of the spring force would be this. Make sense? All right, and then at the end of the day last time, we derived the fact that if I have a spring that's either compressed or stretched, that there's some energy that it has, and the energy stored in the spring, which is the same thing as potential energy, is 1/2 k times the distance stretched squared, or 1/2 k x minus x naught squared, where this is its equilibrium position, stretch position. Yes?
So how do we know which one, if it's a negative or not in front of the k? For
So the negative
force?
just gives you the sign.
So like, if we're stretching it, it's a positive, and if we're compressing, it's negative?
So all that means is like, and I won't even worry, I mean, honestly, I never worry about that. But if I draw a free body diagram for this and I stretch this from its equilibrium position, so if I move it this direction,
The spring force.
then which way would the spring force be?
Opposite.
Opposite, and it has a magnitude k times the distance stretched.
Oh, so it'd be
And
negative.
the negative sign just tells me that
It's
it's opposite the direction I stretched it. Okay?
Sure.
That makes sense to everyone?
It's because all the spring can do is resist. It can't manufacture its own force, right?
Well, I mean, it can have its force, it's just the direction of force is opposite the direction it's displaced.
Okay.
So if I push it, the force is going to be this way.
And if you
I
pull
pull
it,
it, the force is going to be that way.
Okay.
So, make sense? And so I just worry about the magnitudes, and then if I draw a free body diagram, I'll add in whatever signs I need to by hand. Okay? Good. Oliver, I want to go do some stored energy problems. So the spring force, or the energy stored in the spring, can be used when the spring releases to actually to give energy to some mass that might be attached to it. So for instance, an example of this is, let's say I have a cart. These are like the little Hot Wheel launchers or something like that. And I compress a spring, and then I release it. Well, if I compress a spring, there's energy stored in the spring, so PE. And then if this thing's at rest, there's no kinetic energy. After I release the spring, you know, the spring's out like this, and then this thing's moving with speed v. Here there's no potential energy, the spring's not compressed, but I have some sort of kinetic energy here. from much experiment, it's been shown, and you can see this in various other ways, that the total energy stays the same if I consider the spring potential energy as a type of energy. So in this case, potential energy initial plus the kinetic energy initial is equal to the potential energy final plus the kinetic energy final. And I have no initial kinetic energy, no final potential energy. And you can get speed, you can get kinetic energy, and therefore speed of something that was launched by a spring. Does that make some sense to you guys? And so just like with gravity, we can treat the spring force as having some potential energy and treat the total energy of this, which is potential energy plus kinetic energy, as being constant. And we can get a bunch of things like speed of moving objects from that. So let's go ahead and do an example. Let's kind of do this Hot Wheel example. Let's say I have a spring force with a K of 2. So actually, let's say 20 newtons per meter. Okay, and I compress it 3 centimeters. And I have a mass here of about 100 grams. A little bit less than that, probably. How fast would this be going if I compress it 3 centimeters and let it go? How fast would this be going after I launch it? So what I would do with this one is I just look at the initial potential energy of the spring, initial energy. What would it be? One half kd squared, right?
Mm-hmm. Equals.
And then that's equal to 1/2 times k, which is 20 newtons per meter, times d squared, which is 0.03 squared, right?
Mm-hmm. And that's just equal to the kinetic energy, right?
Potential energy.
Yep, and then that's going to be equal to the final energy. By the way, what's the number for this?
The force there.
What's that?
The force there.
So the 1/2 20 newtons times 0.03 squared.
What?
0.3. Are you sure?
That's not what I got.
0.009.
Yeah, I got 0.009. Yeah.
Yeah. Oh, it is.
Point
But I did it wrong.
Yeah, okay. So the kinetic energy final would have to be equal to that. So it'd be 1/2.
I thought that was the kinetic energy final.
That's
Oh, that's potential energy?
Yeah, this is potential energy, 1/2 kd
okay.
squared. That's the
Okay.
potential energy stored in the spring.
Oh, okay.
And then the kinetic energy final would be 0.009 joules, and that's 1/2 m d squared. And so this would be 1/2 times 0.1 kilograms times d squared. And it looks like v would be probably pretty small. What do I? So 0.009 joules. If I divide by 0.05 kilograms, that's what this is, right?
0.18?
0.05. What's that?
Oh, but then you have to
That's
take a square root of it. I'm sorry.
Yeah, square root. So what do I get here?
0.42.
8 joules. And that's v squared, right? Or
Yeah.
Mhm.
meters per second. And then v is what?
0.42.
0.42 meters per second, maybe about a mile an hour. Okay. Is it clear what you would do? All right, here's one for you. Train cars have what's known as bumpers in front of them, which are basically two springs that can compress, and they can run into things and be okay. So let's say that I have basically one spring. We'll do one spring just for attached to this.
Can I ask one question before you move on? On the 1/2 0.1 kilograms, where did you get that 0.1 on the kinetic energy final?
Because that's the mass is 100 grams,
Oh, okay.
and that's 0.1 kilograms. All right, let's say this is K, it's unstretched, but it has a maximum compression of, a maximum compression of 1 meter max compression. This thing is 10,000 kilograms. And we want these bumpers to be good that if this car is going at 10 miles an hour, this is a train car. That if this car is going at 10 miles an hour, or maybe roughly 5 meters per second, that this spring would not compress, would compress, and all the energy would be dissipated in the spring. It wouldn't be added to the spring. It wouldn't go into damaging the car at all.
So at the beginning, is it compressed or not compressed?
Right now, it's not compressed
Okay.
until it hits something.
It
Okay?
just has a mass.
But it
Okay.
can't be.
So this is a mast, it has a bumper. This is its bumper with a little spring. It's actually two springs, but we'll treat it as one. Okay, and it can compress up to 1 meter. We want this bumper to compress that much when this is going at 5 meters per second and hits a wall. And that way it can hit something at that 5 meters per second and not do any damage. So my question is, what is the necessary spring constant? To have this work. So clear what the question is? Car going 5 meters a second, bumps a building. We want or bumps something at the end of the railroad track. We want the spring to compress, and that's all. By 1 meter. So what's the plan of attack for this one?
You still start with potential energy initial equals kinetic energy final to get the K.
Was there any potential energy initially there?
No.
There's kinetic energy initially, so.
Well,
So then
no,
we're going to
because
potential energy final.
What's that?
We're gonna have potential energy
Yeah.
final and no final kinetic energy.
That's right, that's what we want. We want to make it so there's no final kinetic energy. Yep. When it compresses. 1 meter.
We use the
So it'll be pretty much the same type of thing, right?
Mm-hmm.
So what are you going to solve for now?
K.
Okay, all right.
so
I'll give you a minute or two to work on that. You can feel free to work with the person next to you.
So when we're using using the potential energy, we have the 1/2 kV squared. Would the distance squared be the 1 meter then?
Yeah.
yes.
The
Okay.
distance of D would be the 1 meter.
Okay.
D 1 meter. Okay.
That's the maximum it can compress.
That's a lot there. Right. No, I manufactured it out.
Okay. You got it?
Yeah, just once.
Let me know when, raise your hand if you got an answer.
Just a second. Did you get $250,000?
Yeah.
Okay, that's what I got.
Empty train cars.
I can you be
Yeah. Filled up.
What are you doing?
Pushed around train cars.
I have some. If you were waiting on me, because I was like, 1 second.
All right, you ready?
Yeah.
Yes.
All right, so initially, the energy is all, we're gonna start out with conservation of energy. So the kinetic energy initially plus the potential energy initially is equal to the kinetic energy finally plus potential energy finally. Okay, well, initially we have this, the final situation, we want the spring to be compressed so that it's compressed by 1 meter and there's no kinetic energy. Okay, that's the final situation. So initially, there's no potential energy. The spring's not been, there's only potential energy in the spring, and if you're not doing anything to the spring, there's no potential energy. Finally, we want it to be at rest, so that means kinetic energy has to be 0 at the end. And so I'm going to write 1/2 mv squared is equal to, and then potential energy would be 1/2 k v squared. And get rid of those 1/2 by multiplying both sides by 2. And I can see that if I want to solve for k, I'll divide both sides by a d squared. So I get m v squared over d squared is equal to k, right? So plug in 5 for here, 10,000 for here, and 1 meter for here. And when you do that, you should get 250,000 newtons per meter. Everyone get that? Mm-hmm. Good. Okay, now here's one where we're going to combine two types of potential energy. So we've already talked about gravitational potential energy. If I have two types of potential energy, gravity and springs here, I just add those two together, okay? And treat that as a total potential energy. Does that make sense? So here's a situation. I have a spring cannon. I put a ball on top of this spring cannon. Let me see. And then when I launch it, the spring stretches out. And then this thing the ball has some initial speed v naught. And it gets up to some height. My question is, let's say that K here is 100 newtons per meter. This ball is 100 grams. And then this compression is about 3 centimeters. Or let's do 5 centimeters. Okay? 5 centimeter compression, so between here and here, 5 centimeters. Okay. What is the maximum height that, yeah,
Is the 5 the distance of the spring when it's compressed, or is 5 the,
It's like the difference between both.
yes, it's the difference between it's compressed and
okay.
not being compressed.
okay,
So that's the D, that's the distance it's stretched or compressed.
okay.
So the question is, what is the height, maximum height, that the ball gets up to? The projectile gets to. All right, so this one is a little bit tricky, right? So I have a spring cannon firing up a ball. How can I get that maximum height? Do you want to try this on your own, or do you want to get a little, or do you want a little help?
So do
Can
we
we try
add
it
both of
real
them?
fast?
You're gonna have
The-
to find your multiple.
The two potential energies, like MGH and that,
Yeah, we can do that.
1/2 kV square.
That's right. So when it gets up to its maximum height, what's the speed of the ball? Zero.
Zero.
Yeah, because.
Right? So it has some sort of potential energy, doesn't it? No?
MGH. When it's coming down.
So let's talk about, I guess, height above this point here, height above its initial position.
Ground or marshal?
I would take this place as the initial position. So the height above where it started. So think about this problem a little bit, and I'll give you a minute to see if you can get the answer, okay?